what I'm going to do today is talk to you a bit about iterators, because I just love them, and I found an interesting context that I hope you will find also interesting of how we used iterators recently to analyze a social network. And I'm going to be using two separate laptops, so this is going to be fun. I'm going to be using some live coding here and slides there. But first I'll talk a bit about us. So we're Code Institute. We're an Irish company founded about 5 years ago with the purpose of trying to bridge the skills gap. So as you all know, software is pretty much eating the world. There's a ton of software jobs out there in any kind of industry, and we're here to create a faster, more satisfying, more practical path into coding. We currently have about 1,500 students from across the world, different time zones, looking to change careers, usually doing it while working full-time, spending about a year on our course. They're highly motivated, but it's still a very difficult journey, right? Learning development, and specifically full-stack development. And we're trying to do everything we can to support them. So we have a student care team, we have tutoring that we're currently scaling to 24/7. We have industry mentors, but the most important thing that we found is actually having students support one another. Right? So those 1,500 students of ours, we've set up a large Slack community for them. By the way, so who here is using Slack regularly? Cool, okay, so 2/3 of you. So Slack is an awesome platform for chat and for collaboration, and we see that about half of our students are active on Slack on a weekly level, with over 2,000 messages on a typical day. So they would use Slack to ask questions, to answer questions and kind of gain confidence in solving problems, to tell one another about their victories, their frustrations, and just get that sense of camaraderie. Right? And we are always looking for new ways to leverage our Slack community to help people help one another. Right? So we're looking to find who are the influencers on our Slack community, and get in touch with them and give them additional help. And we have a channel lead role. That's kind of the biggest thing. So on our main channels, we would choose the students who are most active already and empower them to do sessions and support our students there. And it's quite difficult to find who are the most active people, right? So we have basic metrics, but we're looking at something more. We're trying to find who are the influencers. So in this project, what we did is created a really cool dynamic diagram to find who is talking to one another. What are the social networks that we see on Slack? Right? Slack itself doesn't have any concept of a social network. There is no friends or connections. The only thing it has is mentioning one another with the @ sign. Right? So you can do @ username, and that will then allow you to notify that person and have a sort of conversation. So that's what we've done with this project as part of a much larger project of analyzing community sentiment. We've created this tool that will help us map the connections between users using those @ mentions. So that's the context. And what I'm going to do in the rest of the talk is kind of half case study, half lesson on how iterators work and why we found them useful in writing this solution, and then what we can do with this. Okay, I'll be doing some live coding later, but I'll start with just a general introduction to these concepts. Just as a show of hands, who of you have used all of these and feel kind of comfortable with how these work? Okay, cool. So that's about a quarter of you, so I hope the rest of you, and maybe you guys as well, will find this interesting. I hope that you'll kind of find how cool this is to solve different kinds of problems, and that you'll see new tricks that you might not have thought of. So I'm going to be using Jupyter Lab for this, which is an amazing tool. And I'm going to start with just the basic concept of iteration. All right, so let's say I'm doing this loop for x in the list 1 to 3, print x. Right, so this is the most basic possible Python loop. Right, I've asked it to go over a collection and do something with each of the items. Right, this works. Another thing that works is if I have a tuple, right, so this works on any Python collection, right? Python doesn't care what kind of thing is behind the scenes. It doesn't work if it's not a collection, right? It's not iterable. And it does work even on stuff like sets. Right? So let's think about this a bit. What does it mean to iterate over a collection? Right? In this basic case of a list or a tuple, this is relatively simple. So like in other languages based on C, where you would have like for I equals 0, I is smaller than something I++. So you can imagine there being an index, right? And we're going with the index from 0 to the length of the list. So that's easy. But what happens in this case, right? So there is no index in the set, right? If I try to ask for the second element in the set, that doesn't work. But Python still knows how to do this. So here comes the concept of the iterator protocol. This is something that's available in many modern languages, but I find that Python's approach here is much cleaner and nicer to work with than pretty much any other language. So what Python does is that when you do something like this, or when you do some other operations like sum, right, so this would also take any kind of collection, what it does behind the scenes is that it asks it to create an iterator. So it uses this iterator function, iter, and it gives us a new kind of object that will then create a sequence on top of something that is not necessarily a sequence in itself, right? So a set doesn't have an actual order, but when I ask to iterate over it, then it's created through this concept. So this is supported internally with pretty much any collection. And the way it works, so iter is kind of a wrapper, but behind the scenes, so you're familiar, it's this method called iter. So it's all working for these magical dunder methods. And this works the same on any kind of collection, right? So let's go for a list, for example. Right, so I'll get a different kind of object, which is a list iterator, but it works exactly the same way. Same for tuple, same for dictionary, same for files, which I might mention later. So what is it? What is this thing? This is something, right, that you need to be able to get elements out of. And Python has a really clean interface here. So for something to become an iterator, and that's something you can easily create yourself, you just need to implement one thing. You need to create an object that has an next method. Okay, so let me assign this, right? So it now is an iterator over a tuple, and the only thing it has is this, right? It.next will give me the next element in the sequence, and then whenever I ask it again, it gives me the following element. So the important part here is that it's got state, right? Every time I do something, the state changes to move along the iterator, and when I'm done, this is the second part and kind of the last part of the iterator protocol, is that when there's nothing more left, we say that we've exhausted the iterator, and it raises the special exception called stop iterator. And this relatively simple thing gives us the power to do iteration of any kind, right? So this will then allow us, right, to do, for example, that sum I showed you earlier, right? If I try to get the sum, it will give me the sum of all elements, but I've exhausted it, right? So the iterator is stateful, so there's nothing left. If I create the iterator from scratch and ask for the sum, then I'll get the actual sum. Right? This works on any collection in Python. So far, so good. We've looked at collections that have all of the elements, and we just asked to iterate over them. What I find now to be more interesting is that you can do it lazily, right? So laziness is perhaps the best quality in a developer, right? So it doesn't actually need to have anything behind the scenes. So let's think of something like range, right? So if I do range 10, right? So that's something that, of course, we can iterate over. And again, right, let's try this as an iter, right? And then I can do next, it will give me 0, and so forth, until I get to 9. You might imagine, and some beginner developers imagine, that when I create a range, then it actually creates some collection of the elements from 0 to 9. But that's not what it does, right? And I can actually give it some ginormous number, and there's no problem. It doesn't create anything behind the scenes. This is the lazy iterator, right? So it only gives me those elements when I explicitly ask for them, but otherwise they don't exist. And this is really cool and gives us a lot of power in creating pipelines, which is what we've done in this example. There's a lot of examples of lazy iterators. Whenever you're working with an external data stream, so usually that would be a lazy iterator. And a common example would be a file. So if you have, I'm not going to show that, but if you open a file and do a loop over the file, it will iterate over all of the lines, and it will do that lazily, seeking in that file and paging that into memory only when needed. Right? So you can open, again, ginormous files and don't care about them. That's laziness. And this is supported by every built-in data type and most other ones that you find in libraries. Has any of you built a custom iterator class from scratch? Okay. So you generally don't need to, like that's something I've done in a specific case, but usually you don't need to because there's this cool thing called generators, which does it for you. So the way that works, for those of you who haven't done that, is, you know what, actually I'm going to show you another lazy iterator and then I'm going to jump to the generators. There's something I want to tell you about this awesome module. So import iterators. So this is part of the standard library. And it has pretty much anything you may imagine regarding working with iterators. Connect multiple iterators, create new iterators, work equally well with finite and infinite iterators, lazy ones. And one that I particularly like is count. So this is something that I use often, and I'll use in the example later, where this count function creates a new iterator across all natural numbers, right? So it will give me 0, 1, 2, and keep going. This is an infinite iterator, right? And of course there's nothing behind the scene. It doesn't use any memory, just remembers the next integer. Okay, so now generators. So how do you create these kinds of lazy iterators yourself? So the easiest way about it would be with a generator function, which is a regular function. So my generator, it's a regular function, but it doesn't return, instead it yields. Right? So let's create a generator that will yield 1, then 2, and then 3. Right? So this is the example I like. And maybe let's even do a fourth one. Okay, so how does this work? Right, so when I run this function, it doesn't actually do anything behind the scenes except create a new iterator, which I can then iterate over. Right? It gives me, right, so it runs down to this part, yields that, and then pauses. Right? Do it again, runs the next one, pauses, next one pauses, next one pauses, and then when I try it again, then raises saturation. So this allowed me to create a new iterator without having to create that iter method myself, sorry, that next method. And it's an extremely powerful case of the more general concept of a coroutine. So my main routine that I write the rest of my program in, then interacts with it, while this stays alive, waiting for me to ask for the next input. And I can easily use this to create that count example. Right, so let's say I want to create my own count. Right, so what I would do is something like initiate a new integer, a new index, and then in an infinite loop, just do yield I, increment I. Right, so let's try that. I count. So I find this to be extremely cool. Right, so if you look at it, right, if you've seen this in any other language, or even just in basic Python, you would think, oh well, I've created an infinite loop, this is going to cause problems. But of course it doesn't, because it's a coroutine that will just wait for you to ask for input, right? It's lazy, it doesn't do anything unless you explicitly ask it. And there's just two more things I want to show you before going into the actual case study. So one is this cool thing that you don't actually have to wait to do them one at a time. You can yield a iterator. So I'm going to show you an ugly example, and then I'm going to show you the cool example as part of the code. So nested generator. Right. Let's say yield 1, yield from, and then I can give it another iterator. 4. Right, so that's that. And so first time it will run until 1, and then it will just give me the elements from here. So it kind of delegates this to another iterator to give me additional flexibility. So we'll be using this a lot, and this is particularly useful for nesting deep structures. And this is actually extremely powerful, so behind the scenes there's a lot that this can do with this concept of coroutines. So if you're doing asynchronous programming, you can actually send stuff to the coroutine. I'm not going to go into that, but it's interesting to read about. Oh, and just one more thing. So if you already have an iterator and want to do something with it, then you actually don't have to create a generator at all. There's this thing called the generator expression, which you might have seen, which is the same as a comprehension, but with round brackets. Right? So let's say I'm interested in the squares of natural numbers. Right? So I for I and range 10. Right? So I already have an iterator, and I just want to transform it to get the squares. Create an iterator. This does nothing, right? And then I can lazily get them one at a time. Right? So this is really nice. And another thing, actually, I'll show you before continuing. I really enjoy this stuff. Is that there's a lot of other functions that you can use to work with these iterators, and you can easily transform them to anything else. So this would be an easy example, right? So convert it to a list, right? So list can eat any iterator and convert that to a list. So it would take the remaining that I haven't put in yet and just create a list. And of course you can do a sum, right? So let's say you sum it, so there's nothing left, obviously. But if I write it again, so I squared for I in range 10, right? So this works. And note that I don't have any brackets around this. So actually the default comprehension in Python is a lazy iterator. So if you don't put any brackets, it just works lazily and doesn't take up any memory. So that's it. Okay, and now let's actually go back to our case study. Okay. So what I want to do, right, looking again at this previous slide, is create a diagram, a node and edge graph, to show all of our students' interactions on Slack. Right? Who is mentioning whom? This is obviously going to be anonymized, right? So I'm using these S integer as a way to not show you actual user IDs. What do we have? So we have a really nice API in Slack, but it doesn't have that concept of relationships. What it does allow us to do is just to get messages, and either get all of the messages, which we usually don't want, or do a search to get a subset of messages. So what we'd like to do here is to do a search to get all messages that would have a mention of another student, right? And then apply some processing to them. The naive approach might be to just fetch the entire data set. Right, so first off, like that's something that I wouldn't want to do, and there's two reasons for why I wouldn't. So one is that that's just a lot of memory, lots of megabytes of memory that I don't have to download at the same time, right? I don't have to store at the same time. And the second part is that there's a lot of personally identifiable information that, again, I would prefer to not handle if I don't have to. So I prefer to get as little of the information as I need at a time, process it, and immediately discard the rest. And that's what we're going to do here. And another part is that you can't actually get all of the data in a single API call, right? So there's a limit. In Slack's case, the limit is 100 messages at a time, right? So we have to page through that result set until we get all of the messages we want. And that leads in then to our approach. Okay, so I'm going to keep this here on that projector, and I'm going to show you how we did it here. But first I'm going to do an overview of the whole process. Okay, so what we've done here is created a data pipeline inspired by the Google or Hadoop MapReduce approach, where we start with the Slack API. Is this working? Yeah, kind of. Okay. Started from the Slack API, fetch the pages, extract from each page the specific messages. Right, so we don't want to work with pages of 100 at a time, but with individual messages. And then extracted again the tuples of who is mentioning whom in the messages, because a single message may mention multiple people. Then reduce them to get a count of how many times each student mentioned another student. And then once we have that counter, to render that into a graph. Okay, so I'm going to be going over the stages here, and I'm going to be showing you the code. Okay, and I'm going to share this on GitHub at the end. So let's start with the imports. Regular operating system, standard library imports. So we have the OS module, which we don't actually care about. We have some stuff from collections that I'll show you later, which I really like. There's that count, which I'll show you in a bit. Regular expressions. This actual Slack API. Network access is something that I'll talk about at the end. And graphviz is our main visualization library, so that's what I use to create the chart. And if you find yourselves actually trying to use APIs like this in Jupyter, then you need to use this because Slack's API uses an async IO loop behind the scenes, and Jupyter does as well, and they don't play well enough unless you nest them. So that's a library that solves that problem. Okay, so we'll start with the Slack interaction. Okay, so how do we get the data from Slack? So obviously we need to have a token, so a secret token for our Slack organization. We can do 100 at a time, and what we're going to do in this case is just ask for all of the mentions, so something that starts with an @ sign, right, during the last week. I was actually hoping I'd be able to show you the API in practice here during the talk, but the network has been really poor, so I'm not going to try that. I have the data preloaded. But otherwise it would take, in our case, it would take about a minute to load all the messages I want. Okay, so this is, for me, this is the really fun part here, right? So the naive approach here might be to do an infinite loop until you've gotten all the results, or might have been to get the first result and then see how many pages there are. But I prefer to think of that, right? So if you look at the slide there, so I prefer to think of it as actually starting with the natural numbers as our first data element and mapping each natural number to the results page for that number, right? So we're mapping 1 to the first 100 results, mapping 2 to the second 100 results, etc. Right? So for each page, we get the data corresponding to that page. And then, right, immediately, I could have done yield all the matches, so that list of messages from that page. But instead, I'm using yield from to immediately get 2 birds with 1 stone. So instead of just getting the pages, I'm getting the individual message objects. Right? So I'm getting a stream of all single messages. And this is going to go for all pages in the natural numbers, right? Which actually I don't want, right? Because that would be infinite. So I'm breaking this once I've gotten beyond page count. Right? So as long as I'm good, I keep yielding, and then when that's done, this will break, and I'll get that stop duration. Okay, so this gets me a stream of all message objects. And yeah.
You also get message strings?
Yeah. So it has some additional information. It would have something like the previous message, the message before, and any metadata. So there's a lot there that I don't care about. So that's actually that personal identifiable information that I prefer to immediately discard. But no, we are actually looking to see if there's any other information that might interest us in different kind of analysis. The one thing I want to show you here is just to prove that this is lazy. Right? So I've mentioned that if I actually wanted to run this in a naive way, then this would take about a minute. But if I just run the function, fetch user dimensions, then that doesn't take any time. So it just creates the iterator and doesn't actually go to Slack. Right, so that's the first part where we covered about half the data pipeline. And then the second part is a tiny bit harder in the Python sense, and that now we need to extract those tuples out of each message. Right? So a message is a string where we have one or more mentions starting with an @. And here to extract them, we've used a regular expression. Right, so as the quote goes, regular expressions are like violence. If it doesn't work, you're not using enough of it. So that was the natural approach here. using a capturing group here, and then on each of the messages using the find all method to get an iterator of all of the matching IDs. Right? So this is the main part. So for each of the messages, right, that's our next phase. So for each message object, we're gonna transform that into a sequence of tuples, right? We have the messages offer. We have, through that regular expression, all of the user IDs that they've mentioned. And now we want to create a tuple pair of who mentioned whom, right? So that's this generator expression, right? And the only part here that I haven't mentioned yet is this anonymizer thing. So this is something that I also really like. Okay, so it's just this, right? So if you ever had a situation where you wanted to anonymize some data set, right? There's a lot of ways to do this, but I couldn't find any way that's cleaner and shorter than this. Default dict is a object in the collections module in the central library that will create a dictionary that would never raise a key error. It would just make the value on the spot. Right? And the way it does it is that it takes as its argument some callable, and will call that callable to get a value. So this is the regular use case, which I'll actually show you a bit later on in this code. Right? So if I have an anonymizer that just has int as its argument, then it starts off empty. Right? So it's default dict of type int. That's currently empty. If I ask what's the value for 1, then it will tell me 0. And if I ask again what's in there, so it has mapping from 1 to 0. Right? If I ask what's an anonymizer of whatever food, then again that's going to be 0 because it's called int. Right? And now it remembers both. So it just creates them on the fly, giving them values. This is useful for different kinds of counters, accumulators, but obviously this wouldn't work for an anonymizer because I want them to have different unique IDs. So that's where that rest of the code comes in, right? So what I've used here is that infinite iterator of count, and I've used that next method, right? So next will, in a stateful manner, every time give me the next natural number, right? So the way this works is starts off empty. This is a bit ugly because it doesn't have a nice representation, but like look at just this part, right? It starts empty. Then I ask for a value of, let's say, foo, right? So that's going to be 0. And then I ask for the value of bar. That's going to be 1. Then I ask for the value of as. That's going to be 2. And then I ask for the value of foo again, and that's going to be 0. Right? So as I ask for them, it creates these on the fly and will remember them for as long as this stays in memory. So I find that to be really nice to work with stuff like this, right? And then for that tuple, right, for this part of the data pipeline, then what I'm returning is not the actual user IDs, that might be a bit sensitive, but they're anonymized IDs, right? And that's pretty much it. So we've gone through this pipeline of getting the data from Slack, putting it in the right form, where now we have a lot of these small tuples, each showing us a mention, right? And then the last part is that we actually want to count them. We want to see how serious, in a way, is the relationship or the influence between a pair of students. And then the solution is extremely easy. Just use the counter object, right? So this is another object from Central Library. How many of you have used this one? Okay, so about half. Cool. So I'm happy to see that this is more popular. This is one of the nicest things in Python. So if you ever have to solve Python questions in an interview, this will help you shorten many of the questions by 2. The way this works is that it can eat up any sequence and spit out how many times each element in the sequence appeared. Right? So 1 appeared 3 times, 2 appeared 2 times, 3 appeared 2 times, etc. Right? So obviously this would work for something like a list, but it will also work for a lazy iterator, right? It doesn't care. So Python's iterator protocol abstracts all of this such that everything that has to iterate would work with any iterator. For example, if you were ever curious about the units digits of squares, right? For example, I know I have for I in range, let's say 1,000. Right? So you might be interested to see that there's 100 numbers ending with 0, 200 ending with 1, 204. Right? So there's some interesting pattern here, and there's no squares that end in 3, 5, or 7 or 8. That'd be cool to know. So whenever you need to count something, this is your friend. And because this is the exact thing that we want to do, right, we just use that counter, and that's the whole operation. Right, so we had these two generators, right, these two iterators that will get us all of the dimensions and then transform them to the shape we want. Right, so this first part, so we're composing two iterators. This takes no time at all. And then I'll just feed that into the counter, it eats it up, right, and it will lazily get all the data it needs, right? So once it's finished processing the previous element, it will continue getting the new ones. Right? In this case, I ran it yesterday, it took about 34.1 seconds. So it's highly dependent on how busy Slack's servers are. So it's really funny that doing that query with, so this is my query at asterisk. So this might, in some cases, take like a couple of seconds. In other cases, it might take 10 seconds, just because it apparently needs a lot of processing in their backend. Anyway, what it gives me is this. Right? So I get a counter of pairs and the weight of that pair. Right? So this tells me that student number 0 mentions student number 1 once. Student number 2 mentions student number 3 7 times, etc., etc. for each pair of students who have mentioned one number at least once. And then if they haven't, then that's just going to be 0 for my use case. Okay, and that brings us to that final part of actually charting a nice graph for it. There's different approaches here. I specifically like the graphviz library, so it's something that's available for free in Unix. You can also install it on Windows, as I had to do in this case, because I wanted to work on this laptop. And what it does is that it eats up a sequence of nodes and edges that can have different kinds of attributes, and then will plot, right, a nice graph to show you how these nodes are connected to one another. And the thing that I really like is this part, so overlap false. So it will do some really nice maths behind the scenes, a lot of iterations to create the best possible layout where edges never overlap a node. Okay, so I'll show you that in a second, but let's go over the code first. Right, so I've asked it to render the dimensions counter I have. Right, so I'm creating a new directed graph, right? Directed in the sense that there's going to be arrows there because this mentions relationship is unidirectional. So student A, my student mentions student B many times, while the other didn't get back to that at all. So we need a directed graph. We're going to be rendering that as an SVG, which is really useful. The main part here are the edges. So that's a direct transformation of our mentions. Right, so for each mention, we have who mentioned whom, how many times. So we just go ahead and create an edge for that, so an arrow, with the width, right, being just the mention count. Okay, and I'm just adding these S prefixes to make it clear that it's a student with that ID. So that's going to be S0, S1, etc. So this is the edges, and for the nodes, we don't have direct information for the nodes, but to make this a bit nicer to look at, I've decided to go ahead with making the area of the node proportional to the total number of mentions that they got across the chart. So here I'm using that default dict with an int, right, just to aggregate, to count how many times each student was mentioned overall. Right, so creating node weights. And then for each node, creating that node object with a size, I mentioned being proportional to the number of mentions, right? So because I have to work with the width and height, I'm taking just the square root to make the area proportional. Making the font size the same, And that's it. So I'll go ahead and render this. This only takes a couple of seconds. And we get this cool thing. Okay, so let me show you how this works. Right, this is pretty much the same screenshot from before, but with new data. This is actually huge, so this is zoomed out. The original size is this. Right, so let's go back out. I have here as nodes, as circles, each of the students, with a tooltip of how many times in total they were mentioned. So that was that aggregation with the node names. And we have the arrows being just the result of that counter. Right, so for each element of the counter, we have an arrow that has, right, student 10 mentions student 3 19 times. Right, and what this allows us to do is to understand at least a bit at a high level what are the dynamics across the entire community. So we can look at this on a week-by-week basis or whatever, right? We've been experimenting with this to see, okay, so this student is being asked a lot and they're responding to everyone. Or this student might be getting approached a lot, but they're talking to that other student who other people don't talk to, but this person is. And then we can combine that with what we already know about our community to try to understand who's really active there and in what way, and then reach out to them and support them and give them advice and promote them to channel leads. So this is something we've been playing with a lot. And something that I've played with yesterday is adding some color. So this is entirely new. I was thinking, so we have here as the node weights the number of mentions immediately, right? So how many times they were mentioned. But maybe we could get some more holistic data here. And what I've done is that I've played with this library called Network X. Right? Network X is a really nice library, not an external library, that does different kinds of analytics on networks like this. So it's focused on any kind of network, but especially useful for social networks. And one of the tools it has is an implementation of the PageRank algorithm. Right, so that algorithm created by Larry Page when they formed Google, right? So to understand which pages on the web are more influential. So it doesn't look just at how many links a page gets, but whether the links that that page has are coming from other influential sites. So that's self-referential. And behind the scenes, it iterates a lot to try to find a stable value that's actually an eigenvalue of the matrix that represents the connections between them. And that's what we did here. So right, students mentioning one another, pretty much like web pages. So I fed that into this Network X directed graph. This is, by the way, very similar to graphviz, and I could have actually used Network X to do the chart as well, but it just doesn't have that nice layout, so it cannot solve for not having any clashes between the edges. But it does create that PageRank. So calculated it, normalized it to be in the range 0 to 1, and then graphviz allows us to color nodes in the HSV space. So what I did is just have the PageRank control the saturation. So this is this newer version with the deepest red being those who are most influential and more holistic level. Right? And you can see a bit on how influence kind of flows between students. So this is the most influential. Right? And there's a lot of others who were influential in some circles. So that's pretty much it. This is what I wanted to show you. We've been playing with this a lot and are still looking for ideas. And I'd be happy to take any questions from you about iterators, about this, and maybe any suggestions you have for stuff that you've done that's similar and you think that would be cool for us as well.